Good afternoon, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Networked Intelligence at the Robert Bosch Center for the Cyber-Physical Systems, IASC. Today's talk is by Professor Boris Grot, and he will be speaking on enabling serverless research with the vHive open source ecosystem. Boris Grot is an associate professor in the School of Informatics at the University of Edinburgh, where he leads the EASD lab. His research focuses on understanding and alleviating efficiency bottlenecks and capability shortcomings of processing platforms for data-intensive applications. Professor Boris is a member of the Micro Hall of Fame and a recipient of multiple awards for his research. He is the program co-chair for Micro 2022 and the general chair for HPCA 2024. Before we move on to the talk, we would like to request the audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. I'll be pasting the links in the chat box. Please do check. Finally, we request the audience to please keep your microphones on silent for the duration of the talk. And if you have any queries or questions, you may directly raise your hand and Professor Boris will let you know. Over to you, Professor Boris.
Great. Thank you very much for the introduction. Thank you for having me. It's a real pleasure and honor to talk about my research with you guys. So I very much welcome questions during the talk. Actually, I have quite a bit of content, but the content is quite modular. So sort of we can adjust how much technical ground I cover based on how many questions there are. So definitely, please don't be shy about asking questions. There's no concern about spending too much time on questions. I'm very happy to pause and discuss things. Okay, so let's see. So obviously, as the title says, this talk is about serverless. I'm not sure how many of you are familiar with serverless. So let's start with a brief overview of what serverless is and why it makes sense. All right, so let's see. So historically, if you wanted to host some sort of an application on the cloud, right? And let's suppose that this is a non-trivial application, right? This is something meaningful. Maybe you're running a website, you're trying to sell things. So there's a database and there's a front end and there's a bunch of kind of business logic and accounting logic and so forth in order to power the website. You would rent a really big, powerful instance, the Amazon cloud, Google cloud, Microsoft cloud, whatever, right? And you would package everything up as a really fat virtual machine and run it on a node with a lot of memory and a lot of CPU horsepower. And that's what you would do. And if it turned out that one node is not enough, you would replicate everything. And so then you would run, this entire super fat big memory virtual machine in another node and in another node. Now, this is completely fine, but the problem is that these nodes are very expensive. It's very difficult to scale things at this really fat granularity. It's also a fairly non-responsive sort of way to scale because in case there's a traffic spike, it will take a lot of time to replicate this big memory virtual machine, okay? Also, anytime the traffic dies down, the developer or whoever is operating this virtual machine will have to pay for the idle time of the virtual machine. In fact, the amount of money they have to pay is about the same as what they would pay if the service is operating at peak capacity, right? This is a really non-responsive way to do business. So in response to this, a lot of the developers, a lot of the sort of users of the cloud have moved to a model called microservices. Now, the idea of microservices is fairly straightforward. And it's, let's take key dominant components of the logic and break them up into completely standalone pieces, right? So in this picture, there's a bunch of front-end logic, right? So this is sort of maybe the user interface of the website itself. And then we have a few different sort of key components, right? So we have maybe the accounting, we have the catalog, we have the recommendation system, right? And all of that is backed by a database, right? And so all of these services can be operated completely independently. And one of the really nice things about this is that services can be scaled individually. Okay, so in my example, let's suppose that the recommendation system is, I don't know, powered by some like super complicated machine learning logic. And so it consumes a lot more CPU power than other services, right? And so in order to scale that, maybe I can deploy multiple instances of the recommendation system, but it's only the recommendation system that I need to scale in this particular example. Okay, so this is good, right? Because now I can sort of scale things at the service granularity, but the problem still is that these are still fairly beefy services, and they still run in traditional virtual machines on rented instances. And so anytime, again, my service is idle, even if I scale things back down, I have to pay for the virtual machines that are sitting idly, right? And it also takes me a fairly long time to spin up one of these individual services if the demand spikes. Okay, so the trend is basically toward even greater modularity and disaggregation in the cloud. And so kind of the limit of this, which is what we're witnessing right now, is the serverless model. Okay, and so kind of as this picture shows, serverless model goes even further than microservices in breaking up logic into really small bits and pieces and running and scaling each of these bits and pieces completely independently of each other. Okay, so let's talk a little bit about serverless, okay? So essentially, serverless, also known as function as a service or FaaS, but I'm gonna keep using the term serverless to avoid confusion, basically is a way to run large applications as a collection of stateless functions. Okay, functions are invoked on demand via triggers, which can be, for example, a user clicking or entering something in a web form, or can also be invoked by another function. So functions can call each other, as this graph shows. Let me actually turn on a pointer here, right? So functions, a function can call another function and so forth. Okay, functions are stateless. And in fact, it's the stateless nature of functions that gives rise to the really confusing name serverless, right? I mean, like serverless, like what does it even mean? Like everything runs on a server in the cloud, right? But it's because functions are stateless, I can shut them down and then I can spin them up on another server and everything works correctly. Now, just because something is stateless doesn't mean that my application cannot have state. State is there. And in fact, again, this picture shows it, there's a database, but the database is completely separate. It's not part of the function. Okay. Those of you familiar with, for example, Amazon infrastructure, somebody can use Amazon S3 for stateful storage, while, the application itself is actually serverless. And so all of the functions that comprise the application are stateless. Okay. Yes. Premal, please.
Yeah, so just to understand, like, so when the spike, there's a spike in the demand. So what happens in this case? Would you?
Yeah, I'm going to talk about this. I'm going to explain this. Okay, so basically the stateless nature of all of this facilitates on-demand scale in and scale out, where basically, so scale out means I'm going to make more instances of my function. Scale in means I'm going to shut them down. But what's really cool with the serverless model is that because everything is stateless, all of the functions themselves are stateless, I can shut all of them down. Okay, so I can actually be operating an online service, like a web store, right? Where at any given time, there's absolutely nothing running, and I'm paying zero money because as a developer who is running in the cloud, because nothing is running. Okay, now, of course, there's a database. My store has a database, right? And so if a request comes in, the cloud provider, so Amazon or Microsoft, will spin up the functions on demand in order to deal with the request. And to answer the question, again, the cloud provider will spin up as many instances of the functions that are being invoked completely on demand based on the traffic. So if there's a massive traffic spike, the provider will spin up, some number of instances, whatever is necessary to deal with the traffic spike. So the cloud provider manages all of the infrastructure, 100%. I have zero control over this, okay? But they're responsible for this, right? And so And so the developers pay only for the invocations. So they pay for the CPU time that the function consumes while running, and they pay for the memory that each of the functions takes up, not for the idle time. This is a key fundamental difference from any other deployment model in the cloud. Traditional virtual machines, microservices, they operate differently. While a virtual machine is running, regardless if it's idle or not, you have to pay money. Okay, so hopefully the question has been answered, Parimal. If it's not clear,
No. So I sort of understand. So somehow you're saying that when the demand goes up, mostly the traffic can be, sort of handled by these how do you say, these functions, stateless functions, right?
Right.
You maybe have like more databases because you do need to store more data if the more demand is coming, right?
So that's not necessarily true. I mean, again, if you think about a traditional deployment using virtual machines, right? So again, I have some sort of an online store, right? So, I mean, that infrastructure also has to be able to deal with traffic spikes, right? So not only do I somehow have to make sure that the database is scalable, right? But all of the other logic also has to be scalable, right? If I go back to this picture, I need to scale this entire infrastructure, right? Like monolithically, there's no way to scale it modularly, right? So if I use a cloud database like Amazon S3, again, the cloud provider makes sure that the database is scalable. That's their responsibility, right? So the database is replicated. It's also replicated in order for it to be fault tolerant, right? So that's kind of like some magic that already exists, right?
So if I may,
is the logic. Yeah, go ahead.
If I take a specific application, for example, say it's the big sale event by one of the service providers, right?
Mm-hmm.
And so the traffic is so maybe most of the people who are buying stuff online, they already have an account, so you don't have to really worry about account creation and stuff, right? So I mean, I'm assuming that most of the traffic is that you're making a lot of sales, right?
Right.
So in your example, for example, what functions are the one which you would need to spin up to be able to handle this traffic?
Well, so let's suppose, like there's, like the Amazon store, right? Or some notional equivalent of that, right? So you log into Amazon, right? The first thing you're going to see is, a bunch of suggestions that are tuned to you, right? So that would be the recommendation system. That's very powerful, right? By powerful, I mean very CPU hungry, because this is like some machine learning models and stuff like that, right? You might also see some information specific to your account. So for example, like summary of recent orders, stuff like that, right? Then you perform some sort of a search, right? So you're looking for specific products. So again, so there's some catalog service that's powering that, right? And that's invoked on demand, right? In response to you performing some sort of a product search, right? Does that make sense? So again, all of this is happening on demand, right? So,
right.
As I'm viewing a page, sorry, I'm embarrassed to admit, I actually don't know if there's Amazon in India or not, right? But I'm sure there's like something similar to that, right? And so as you're viewing a page of a particular product, again, maybe there are suggestions of related products that are being displayed on that page, right? So again, for every page, there's a bunch of recommendations that are being generated, right? So this is why specifically I use the recommendation system as like something that you really need to scale very aggressively, in response to demand. Does that make sense?
Yeah. So that example is clear, actually. Yeah. Thank you.
Okay, cool, fantastic. And thanks for kicking off the questions. This is really good. Okay, so like it's clear how the developers win, hopefully, right? So I'm completely not needing to worry as a developer about scaling things, right? All of that is happening magically for me because the developer is taking care of that. And the only thing I pay for is CPU and memory time. CPU time and memory footprint. Okay, so this is super great. Like the developer clearly wins. Why do the cloud providers like this model, right? Like what's the financial incentive for them? Well, what they get out of it is they get very high density and utilization at the server level, right? Remember, if you're a cloud provider, I mean, it's one thing, to have customers who are paying for virtual machines, right? But the problem is if the virtual machine is idle, sure, the provider is making money, but they understand that their resources are not being well utilized. They actually want to get more money out of these idle resources, right? Because they know the resources are idle, but they can't overcommit the resources aggressively with a traditional model because performance can suffer. Okay, with this model, with the stateless model, they can actually really densely pack everything on a server. And so they can actually kind of, in terms of monetizing their servers, they can make a lot more money, right? So there's a real financial incentive for both sides of this equation. Okay, so that's kind of like the serverless model at a really high level, okay? Now, let's see, what's good about serverless today? Well, the good news is deploying simplicity, right? So users basically don't need to worry about deployment. They just run these functions. They sort of express the connectivity between the functions in a very simple programming model, and that's it. And they just like pay for the invocations, okay? There are bad news. There's bad news that comes with this, right? It's not all great. So as you can imagine, starting functions on demand, you know, even though functions are fairly small and compact, there's significant latencies associated with function startup, okay? So this is called the cold start problem. Every time I have to start a function from scratch, you know, there is a non-trivial delay. It's not huge. It's not many seconds or minutes, but it's still there, okay? So this is not really great. So service providers tend to over-provision and run more instances than necessary and kind of absorb the cost of that. Because functions are stateless, communication between the functions is inherent, right? Anything you need to preserve across functions or, you know, within multiple sort of function invocations has to be stored. So again, there's a lot of communication, there's a lot of storage access, so there's another level of inefficiency. And the fact that a lot of functions are packed on a single server introduces a lot of microarchitectural inefficiency. Okay, I'll talk about a bunch of these things in this talk, again, depending on how much time there is. But all of these things really introduce kind of performance overheads and the cost performance and the cost efficiency. Okay, so that's the bad news. So this is kind of like, these are really great research opportunities, but here comes the ugly bit, right? Serverless is a massively popular model in the cloud today, but the problem is that the state-of-the-art serverless stacks are provider-specific and they're black boxes. As a developer, I can use their serverless stacks, but I don't actually get to control it. In fact, I don't even really know precisely what it is. Okay, so the question is, as a researcher, how do you study and innovate in this kind of a world? Okay. So, okay, so kind of like, as I said, industry has bleeding edge, but completely proprietary black box serverless stacks. Kind of looking across in the research academic spectrum, what we find is that the serverless stacks are kind of like lacking, they're incomplete. So I'll give you one very specific example. In real clouds, serverless tends to use virtual machines in order to run individual functions. And the only reason for that is to provide maximum performance isolation, maximum security, okay? If you look at open source serverless stacks, like Whisk, for example, they tend to run containers on bare metal instances, okay? And so the degree of security and performance isolation is lower, and you know, real clouds are not very happy with that sort of a model, right? So there's a disconnect between kind of open source research projects and real industry. Okay, and so, you know, what's necessary is a real kind of full stack, meaningful representative open source framework for serverless research. And that's kind of what we built in my research group. Okay, and so the idea was to take state-of-the-art, you know, kind of the key open source components that are used across the industry and integrate them in a representative stack. And so that's exactly what we did, right? So we used Kubernetes and Knative for cluster scheduling and function deployment at the cluster level. We use Containerd for end-host and container management. We use state-of-the-art micro VMs from Amazon and Google, so that's Firecracker and gvisor respectively. All of these are open source projects. And we used formerly Google's, now it's an open source project called gRPC communication fabric, right? So we took all of these components and we basically stitched them together into a completely open source stack called vHive, okay? So vHive is highly representative of today's clouds. We actually modeled it after Amazon's AWS stack. We had a lot of interaction with the serverless team at Amazon, and we kind of got their blessing, sort of saying, yeah, what you guys built is essentially, kind of like roughly speaking, representative of what they have. I already talked about the key technologies that vHive supports. In addition to that, we support quite a few benchmarking and performance analysis tools integrated into vHive. So this includes, for example, Zipkin, telemetry, so end-to-end, sort of being able to trace a function through its execution. We support microarchitectural profiling on individual servers. So there's a lot of tooling already built into vHive. Let's see, there's quite a bit of uptake that vHive has enjoyed since we released it just a little bit over a year ago. So there are over 20 universities that we know of that have communicated with us that are using it for research and teaching, several companies that are using it for their own research. We're collaborating with a few of them. And the work received the Distinguished Artifact Award at last year's S+. S+ is a flagship systems conference. Okay, in addition to the serverless stack, we also released a complete serverless benchmarking suite called vSwarm. And so that contains a bunch of sort of meaningful real-world applications like machine learning training, inference, analytics, distributed compilation. These applications have different runtimes and function composition patterns, different ways to sort of transfer data around between functions. And so all of them are packaged as serverless workflows. They're ready to run. We're happy to support you guys if you want to use, vHive, vSwarm. So all of that is out there. We also have a bunch of simple standalone functions that are packaged as containerized images that can be run in a full system simulator called Gem5. I'll have more to say about that later in the talk. So kind of everything from large scale systems research to microarchitectural research within a simulator, you can do all of that, using the open source vHive ecosystem. Okay, so that's kind of the vHive overview. Yes, Pritam, please.
Yeah, so one question, you didn't mention any networking stack in this. So are you going to cover it later?
The what, sorry?
Networking.
Networking
components.
The networking stack, no, I'm not going to cover the networking stack. Actually, the networking stack is like completely out of the box, right? Like this, basically we use gRPC, which is a really, really popular framework for packaging and serializing essentially network buffers in the cloud. I mean, it's really popular. But the networking stack is pretty much whatever is used in the cloud today. So it's TCP/IP and so forth. So there's really, really nothing special to this from a networking perspective.
But for moving the data in and out, do you use the standard?
That's gRPC. gRPC.
Okay. Right.
Yeah.
Is gRPC used also for moving data, like the networking? Suppose you are hosting some services or copying the data between the container instances, not from the controller to the containers.
So basically, gRPC is used at the application level, right? So from the application perspective, if I want to sort of move data around, I'll actually use gRPC in order to package it up. And gRPC will invoke the network stack in order to communicate. But actually all of this sort of, for example, like if you know Google's protobuf, right? Again, it's just a way to use a very standard packaging sort of interface to communicate within and across different applications, right? So the actual network stack runs below gRPC. The application communicates at the gRPC level.
So you're still talking about the control plane. I was asking
I'm talking about
plane.
any sort of communication, So if a function invokes another function, it will do everything through the gRPC stack.
Okay. Thank you.
Okay. Okay,
so I have another question.
Please.
Yeah. So does it support multi-cloud serverless, single application using serverless function across different clouds?
No, that's a good clarifying question, actually. So in fact, vHive is cloud agnostic, right? Like it's a stack, right? So it's a complete stack that incorporates all of these technologies. So kind of like focus on this side of the picture. You can run this entire stack on your laptop. You can run it on your own private cluster, so you can distribute it. So you can have one node, which is a scheduler. That would be, Kubernetes and Knative. And then you can have a bunch of worker nodes, right, which are actually running one or more of your vHive-based applications, right? This is a complete stack. You can also take this complete stack and run it in the cloud. But again, you have to understand that if you run it in the cloud, you will be running it strictly at the user level, right? Because ultimately, sort of like Amazon has their own serverless stack. And so anything that you would run as vHive would be actually, strictly speaking, a user level sort of application running in a cloud. So this is the key to understand, right? We're not replacing what's in Amazon, whatever. It's a complete stack that you can run anywhere you want, including on your laptop.
Thank you.
Yeah. But by the way, I will say much later in the talk. I mean, again, I'm not sure the lately kind of, yeah. I gave a fairly extensive overview, I think, to get everybody on the same page, which seems like that was useful. So I'm not sure how far I'll get in the technical stuff, but actually some of the stuff that we've developed, for example, Amazon adopted and they integrated into their own, like actual in-house black box for us, external people, serverless stack as well, right? So there's a bit of back and forth. But again, I think the key thing to understand is this is a complete stack that you can run anywhere. Okay, so what kind of research can vHive-enabled? So okay, so the way I ordered this talk, which yeah, like we'll see if this is a good idea or not, but this is going to be a little bit like kind of lower level stuff here. First, really focusing on a single individual server, and if there's time, I'll talk a little bit about slightly higher level systemsy stuff. So I hope you guys are okay with that. When I asked, I was kind of I was told that the audience is quite broad and sort of like more or less anything in the systems universe is okay. So hopefully you guys are good with this. Again, ask lots of questions and hopefully it'll be interesting. Okay, so let's focus on the execution of serverless functions on a single server. Okay. So there are, again, unique characteristics that are fairly specific to serverless invocations that are quite different from what you'd find with traditional sort of fatter virtual machines, regardless of whether they're monolithic or microservices. So one of these is that functions execute for a fairly short amount of time, right? For example, execution durations of a few milliseconds or less are quite common. I'm certainly not claiming that all functions execute for that little time, but actually quite a few of them do, okay? This is a really short duration. To put it in contrast, the Linux scheduling quantum is something on the order of 10 to 20 milliseconds, right? So this would be like an order of magnitude less than the amount of time that Linux will give by default to an application before a context switches to another application. Functions often have a very small memory footprint. So again, in Amazon AWS, as little as 128 megabytes per instance is what you can actually purchase. Okay, just 128 megabytes per instance. Okay, and also invocations are relatively infrequent at the granularity of seconds or minutes. Okay, and that's that's a characterization that came from Microsoft Azure, which operates one of the largest clouds in the world. Now, you might be surprised saying, okay, if serverless is so great and if functions are so popular, why are the invocations so infrequent? There's actually a really simple answer to this, which is that, for one thing, there are a lot of, if the service is popular, there will be a bunch of different replicas of a particular function and the traffic is spread out. But also, at the same time, if you have a service which is so popular that the traffic is incessant, so all the time you have a nonstop massive stream of invocations, actually the serverless model is not cost effective. Okay, so if you run something for minutes, I mean, it's a completely arbitrary number, of course, right? But if you run something for a long time, nonstop, you have a continuous stream of requests, and you only pay for these invocations, it's much more cost effective to run things in a traditional virtual machine, much more, right? So if you want to handle sustained high volume traffic as a cloud customer, traditional virtual machines are cost effective, right? If you have periodic service that you want to run, right, that's when the serverless model is actually really effective, right? And so this particular combination means that developers are incentivized to run serverless when they're not dealing with super high volume, super sustained traffic, okay, and when they can package things as these kind of small modular entities. Okay, that turns out there are a lot of scenarios. I mean, some people estimate that about 40% of cloud workloads today are serverless, right? So don't feel like this is a tiny niche. This is massively popular, but it's not an answer to everything. Okay, now here is the really interesting implication of this thing from a perspective of a single server. Because the memory footprint is so small, now think about a cloud server today. Typical cloud server today will have hundreds of gigabytes of main memory, right? So you can pack thousands of functions on a server, okay? And the functions, run for a very short amount of time, okay? And so you can pack thousands of them on a server, and that means that there will be a huge degree of interleaving between two invocations of the same function, right? That's kind of what the picture shows, right? So I invoke a function here, a bunch of time passes, I run a bunch of different other functions, and then the same function is invoked again, okay? And so the question is, what are the implications of this model, in terms of CPU efficiency on that particular server? Okay, so what this picture shows is I'm showing two functions. Okay, so one of them is an authentication function written in Python. Another one is an encryption function, AES, written in Node.js. Okay, I'm intentionally taking functions written in two different programming languages. So this is by design, Python versus Node.js. Okay, the y-axis shows the slowdown compared to what happens if I just invoke functions back to back, right? I invoke authentication and again and again and again, back-to-back invocations, right? Versus when the inter-arrival time between invocations is varied on the x-axis, okay? And so as the inter-arrival time increases, in between the invocations of a particular function, I run other functions on that same server, right? And so we can see that as the inter-arrival time increases, I'm interleaving more and more stuff on the CPU, and the performance of that particular function decreases, right? So there's a slowdown, right? So it's about 150% or 1.5x for Node.js. It's over 2.5x for the Python function, right? So the CPI here is really slow down. I'll explain what CPI is later. So basically, there's a dramatic increase in, again, CPI, proxy for slowdown, a dramatic increase in that, on average between these two functions, 1.7x for inter-arrival times that are typical in the cloud, right? Remember previous slide, we said that typical inter-arrival times are, seconds or minutes. Okay, so why is this happening, right? Why is the performance of a particular function, decreasing significantly as the degree of interleaving on a server increases? Okay, so we did that extensive characterization where we compared back-to-back invocations of a function, right? So this is kind of the picture, we're just invoking the same function back-to-back with interleaving. And for this set of experiments, we model the interleaving not by running a bunch of other different functions, but by running kind of a dedicated stressor that thrashes unchipped caches and things like that on the CPU. And the reason why we use a stressor instead of like interleaving a bunch of other things is to be able to do this in a very short amount of time and to have deterministic execution, right? So we can run this experiment many times, right? And can reason about the results. Okay, don't worry about too much about the methodological details of this. Basically, we use a state-of-the-art methodology developed by Intel for understanding microarchitectural effects. We use 20 different functions written in a variety of languages and runtimes, compiled, JITted, interpreted. All of this is publicly available. All of this, you can just take the containers, compile, and off you go running. Let's see. The key thing here that we want to focus on is kind of what's going on here, right? Where is the slowdown coming from? So what this graph is showing is for different functions, right? It's comparing the performance, which is the y-axis, of back-to-back executions, right? That's the best case scenario, to interleave. Now, the y-axis is CPI. CPI stands for cycles per instruction. And this is basically how microarchitects try to understand performance, right? Remember, we want to be able to execute a given instruction in as few cycles as possible, okay? So anything, over a single cycle per instruction is not good. Our aim is 1. In fact, actually, you can even have fewer than 1 cycle per instruction because you can execute multiple instructions in the same cycle, right? But 1 is effectively, you can think of it as, a good case scenario. In fact, for AES, you can even see that we can execute in less than 1 cycle per instruction, right? And the higher the CPI, that means we need more cycles to execute a given instruction. That's bad, right? That means there are stalls, the processor is not working efficiently, and performance is not great, right? And so what you can see is that, okay, so we have 3 kinds of languages here. We have Python interpreted, we have Node.js, JITted, and we have Golang, which is statically compiled, right? This is only 9 functions here. The mean is for all 20 functions. And we can see that interleaving increases the mean CPI for our entire suite of 20 functions by 70%. It's a very significant increase. And the reason this happens is a phenomenon that we call lukewarm executions. So the function is in memory. The process or the virtual machine is running, right? Running in the sense, sorry, it's not running, but it's in memory, right? It's mapped. The virtual machine has network connectivity. It's completely in memory. It hasn't been swapped out to disk. But in between the invocations of a particular function in the interleaved scenario, there's no microarchitectural state on chip, right? So think back to your computer architecture or computer organization classes, right? Processors have a cache hierarchy that are necessary to exploit locality. So there's nothing in the unchipped caches. All of the microarchitectural structures like the branch predictor, right? Things like that, they're all completely cold. And so when the function starts running, everything has to come from memory, and memory is very slow to access. That's what's happening. Okay, so now we're going to really closely see and try to understand where are they, like in the microarchitectural sense, where are we losing the most performance? Okay, so we break down our cycles, individual microarchitectural cycles, into 4 different categories here. So retiring means we're completing instructions. This is where we want our time to go. But we can see that only a tiny fraction of the time we're retiring instructions. Okay, the rest of the time are stall cycles. So we're waiting for something to happen. Okay, so most of the time is spent in the processor front end. Front end means we're fetching instructions. We're trying to deliver instructions to the core in order to be decoded, executed, and so forth. And this is really killing us, and we'll talk more about that. Bad speculation means branch mispredictions, right? And the red is the backend, and this is mostly waiting on the loads and the stores. Well, mostly we wait on the loads, right? So this is waiting for the data to be delivered to the core. Okay, so front end instruction delivery is the largest source of stalls. About 56% of additional cycles compared to back-to-back execution are spent waiting on the processor front end, right? So basically, we're really struggling delivering instructions to the core. Why is that happening? Okay, so this is a lot of kind of low-level microarchitectural stuff. I'm going to try and go fairly fast through this. Those of you who have had a computer architecture class hopefully can understand this. If you have not, that's okay. Just try to go along with this. Essentially, what this graph is showing is the number of misses in the second level cache for instructions and data. Now, processors have 3 levels of caches. Second level is hundreds of kilobytes. The last level is many megabytes. Okay, so this is the second level cache. This is relatively fast to access. Normally, we expect that most of the things we need will be satisfied by the first or second level of the cache. But what we're seeing is that there are over 50 misses per kilo instruction, per 1,000 instructions in the second level cache. This is a lot. Most of these misses are coming from instructions. That's in the back-to-back execution. This is the good case, right? In the interleaved execution, things get a little bit worse, but not a whole lot worse. Okay. But when we look at the last level cache, 25 megabytes, this is a huge, huge cache in our Intel processor. We see that almost nothing misses in the last level cache for back-to-back execution. But in the interleaved execution, we have about 20 misses per kilo instruction on average. In many cases, it's approaching 60 misses per kilo instruction, right? And most of these misses are for instructions. Okay, this is super totally killing our performance, because if we cannot get instructions to the core, we have nothing to execute. There's no work to do, right? It's like you want to study for the test, you need a textbook. The textbook is in the library. You go to a library, you get a book, you go home, you read the first chapter, and then you realize that, you know, for the next part of the exam, you need a totally different book. And you have to go to the library, get the book. And so while you're getting the book, you're obviously not studying for the exam, right? This is really that sort of a phenomenon, right? We're going to memory. It's taking many hundreds of cycles to get the instruction. We get the instruction. And then, you know, a little bit later, we once again have no work to do. We have to go to the memory once again, right? So total performance killer, right? You know, going to the main memory is the critical bottleneck. Okay, so the good news is when we study, you know, the misses for instructions on the chip, we realize that there's a high commonality across function invocations. Okay, and so when we invoke the same function over time, most of the instructions being accessed are the same, right? They're the same in the kernel, they're the same in the network stack, they're the same in the gRPC, and they're the same in the user code to a large extent, over 85% of instruction cache blocks. Okay, so this is kind of like the good news. There's high commonality. The bad news is there's a large instruction working set. So we have many hundreds of kilobytes of instructions, even though the function execution time is really small. Okay, so and that's because there's a deep software stack, right? There's kernel code, network code, the communication framework gRPC, the actual runtime, like Python, for example, and then you have the actual user code, right? So, you know, many hundreds of kilobytes of code. It's really difficult to pack all of this in the processor caches, especially when you have many functions, and that is why, you know, we have a lot of misses for instructions going all the way to main memory. And so that's the problem we want to solve, okay? And the idea, the way we're going to solve this problem is by using prefetching, okay? So we want to basically learn what are the instructions that are being used across invocations and deliver them to the core, deliver them to the CPU ahead of time, okay? That's the basic idea. And the way we're going to do this is when the function executes, we're going to see what instructions are being accessed. We're going to make a record of that. We're going to store that record somewhere. And when that function executes again, we're going to basically restore those instructions by prefetching them into the CPU, and the function will find the instructions in the CPU, even though everything was kicked out to main memory, sort of in between the invocations. I don't expect you guys to know microarchitecture, right? I know this is not a microarchitecture audience, so I'm going to sort of really skip over the details. So we call our prefetcher Jukebox, okay? And so basically what it does is as the function runs, it records misses in the L2 cache and stores the records into the main memory, okay? When the function executes again, it retrieves the recording and prefetches everything into the L2 cache. And it does this completely independently of the core, right? So it kind of just like dumps what it thinks will be the useful instructions into the CPU or into the CPU without waiting for the core, right? The whole thing operates on virtual addresses, and that makes it kind of work very nicely with the existing, I mean, pretty much everything, virtual machines and everything like that. So that's cool. Okay, so yeah, key idea, record and replay the instruction working set in the L2 cache in the CPU. Okay, we simulate everything in a detailed full system simulator. All of this infrastructure is publicly available. And the key result here, again, really skipping over a lot of the microarchitectural details, is that we can improve performance by about 18% on average by covering over 85% of instruction misses going to main memory. Okay, there's a cost to this, so there's a little bit of hardware support that we need. That's pretty simple. You can just take my word for it. We also need to store a little bit of information in the main memory. Basically, we're recording this instruction working set of the functions. We're storing it in main memory. We need about 32 kilobytes of main memory capacity per function instance. This is really a drop in the bucket compared to the memory used by the entire function. So, that's fairly cheap. Okay, so Jukebox, simple and effective. Big picture, serverless functions kind of present new challenges and opportunities for CPUs. We developed this infrastructure called vHive. Using vHive, we did a characterization of what happens when functions execute on the CPU, right? We found that there's a very large instruction working set associated with individual functions, right? There are frequent off-chip misses for instructions when the function runs. And so we can record and replay these misses in order to cover the, in order to improve performance in executions of the same function on a CPU, under interleaving. Okay, so that was kind of the first part of the technical talk. I have another part, a little bit shorter, hopefully easier to understand. But I know we have time, so I'm happy to take any questions on this bit before we move along. Yes, please.
Yeah, so my question is, today we are talking of serverless on GPU as well. So how extendable this solution is for GPUs?
So actually today, as far as I know, in any major cloud, GPUs are not used for serverless. It's not impossible. Research-wise, this is sort of becoming an interesting research direction. People are starting to use, to look at serverless for functions. But the thing to understand is that, remember what we said earlier, if something is going to run for a very long time, serverless is not a cost-effective model, right? At that point, you'll just deploy a traditional virtual machine, CPU, GPU, whatever you want, right? It's really kind of like you have to do a little bit of processing and you want to do it on demand. So it's fairly short intervals of time. That doesn't mean that GPUs are a bad idea, but it doesn't mean that it's probably not for everything. Moreover, a lot of the serverless stack, the network stuff, gRPC, the virtual machine infrastructure, and inevitably, at least some bits of the control code are going to run on the CPU. And so if the function runs for a short amount of time, how much of that is offloadable to a GPU, right? So I think this is why the cloud providers have been slow to deploy GPU support for serverless, is because at least today, I don't think there's a lot of demand for that, right? Again, I'm not saying it's a bad idea. I'm just trying to explain why it hasn't happened yet.
Yeah, no, I agree. But there are private cloud which are providing us
Right.
serverless function on GPUs. Yeah.
Exactly. And there's research that's starting to look at this.
Yeah.
Right. So I'm not saying it's a bad idea, right? I'm just saying that it's kind of a niche within a niche.
Yeah. Thank you. Yeah, I got it.
So I'm just going to get more water. Yep. Go ahead. I think there's another question. Sorry, I can't see all the questions. So please just speak up if you have a question. Okay, cool. If not, we'll move along. Okay, let me switch to the slides. Okay, so what I've been talking about is a phenomenon where a function has been invoked and it's sitting on a server and it's occasionally invoked again and again and again. But remember, a key part of the serverless deployment model is this high elasticity, right? So if I need more capacity, I can spin up more functions on demand. If I need less capacity, I can shut everything down, right? You know, this is not something that YouTube is going to do or Amazon for their main service, right? There's always demand, right? So this is more for like occasional processing, right? If you are a little shop, right, and you're selling some, you know, handmade, you know, some crafts or something like that, and you're running your own little website, this is a good model for you, right? And so what happens when, you know, we need to we've shut down some function instances and now there's some demand and we need to spin up more instances. And so there's nothing on a server, right? Or we need to spin up more instances. And so we need to engage more servers, right? This is called the cold start problem, right? Or cold start, right? We're starting completely from scratch. We need to boot up a virtual machine and so forth. Okay, so I think I kind of covered the introductory bit of it already. And so a key challenge here is spinning up new function instances really quickly. The problem is that spinning up a new instance from scratch is slow, right? We need to boot up a virtual machine. Now, the virtual machines that are used for serverless, they're called micro VMs. They're fairly lightweight. They boot faster than a traditional virtual machine, but it still takes a while to boot. And so what providers are starting to deploy, and Amazon is leading the pack, although it's still not fully not fully available, but sort of it's really moving in that direction, is using a technology called snapshotting to accelerate cold starts of serverless functions. And so the idea of a snapshot is fairly straightforward, right? Once I've booted my virtual machine and I started the runtime that I'm using to execute a function, so for example, Python or Node.js or Java, right? I'm gonna take an image of this fully booted, ready to run virtual machine, and I'm gonna store the entire memory image. And that's called a snapshot, right? And so the next time I need to invoke a function, instead of booting a brand new VM from scratch and then booting, you know, like starting the runtime and so forth, I can just restore the memory image of my entire virtual machine. Okay, so that's called restoring a snapshot. Okay, so this is fairly straightforward stuff. But the question we are asking here is, you know, okay, this is really cool. I can record, you know, I can take a snapshot and restore from a snapshot, but does that fully solve the cold start problem? Okay, so let's first understand how starting from a snapshot works. And I know I don't have much time left, so I'm going to go fairly fast here. The good news is I don't have a lot of slides in this part of the talk, and I think it's a little more intuitive than the previous part. Okay, so here is the stack. Here's where the time goes when I invoke a serverless function. So we have the scheduler, right? So this is like Kubernetes and Knative essentially saying, oh, okay, I have this function, you know, where do I put it in my cluster? Okay. Then we need to load the function state, right? So we assume we're going to boot from a snapshot here. And so we're going to restore the virtual machine monitor, which means we're going to restore the architectural state. That's really fast. That's basically the registers that are used by the CPU. We're going to map the guest memory file, essentially saying, those who know Linux, this is like mmap, right? So we're going to say, okay, here is the snapshot on disk. Okay, and so here is the memory region to which the snapshot corresponds. But that just like kind of like saying, here is, the memory region into which we're going to bring in the stuff from disk. We're not actually going to read it from disk, because that's a lot of memory, some of which is not actually useful, right? We're just telling Linux where to find the stuff on disk and where to put it in memory when it's necessary. Okay, and we're going to resume the virtual machine from the point at which the snapshot was created. Okay, and so that's kind of this blue part here, restore the VMM, and then we're going to restore all of the connections, right, to the cloud database, to the control plane, stuff like that. Okay, and then we're going to actually process the function invocation. And so now what we're looking at here is we're comparing the warm invocation, and that's what we talked about in the previous part of the talk, when everything is already memory resident, okay, to a cold invocation from a snapshot, right? And what we're finding is that, running from a snapshot is about 20 times, that's a lot, slower than running from a warm invocation, right? And we can see that loading the VMM takes virtually no time, and most of the time goes into connection establishment, connection restoration, and function processing. Now, mind you, when we're running from a warm start, we're still processing the function. It's still there, right? But here it's considerably slower. And the question is why? Why is function processing so incredibly slow when we're running from a snapshot, when you'd think, everything is there? Okay, and the answer for this is lazy paging. Lazy paging means we've told Linux how, where the data is in storage and where to put it in memory. But actually what happens is as the function starts executing, it experiences page faults, and it needs to bring the data on demand one page at a time. And so there are disk accesses that occur. Disk is incredibly slow. I think everybody understands that, right? And so we have these serial on-demand, one-by-one disk accesses where, we're kind of bringing the stuff into main memory. By the way, this includes instructions and data, kind of everything is slowly coming from disk. Okay, guys, same idea as the previous part of the talk. We look at the commonality. Now, in this case, we're looking at memory, entire memory footprint of the function. And we find that most of the pages used across invocations are exactly the same. That's the blue bit. Okay, and the red bits are unique across invocations. And so the idea is, hey, why not record the set of pages that are being used across invocations of the same function and prefetch these pages into main memory? Before we're talking about prefetching instructions from memory into the CPU. Now we're talking about prefetching from disk or over the network, so from cloud storage, into the main memory ahead of the pages being actually touched as the function is executing, right? So we can see there's a lot of commonality in the pages being accessed, okay? And so we can record and prefetch the pages, right? Guys, there are very few tricks that systems people use, right? This is one of these common tricks, okay? So as the function executes, we're gonna see which pages are being touched. We're gonna record the set of pages that are being touched. We're not recording the content, we're just recording the actual metadata about the pages. And when the function executes again, we're going to read our working set file. So that just tells us what pages we need. We're going to read the pages from disk one by one, just like boom, 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 right? And we're going to actually load the content of these pages into main memory before actual usage by the CPU, right? So again, because we're running out of time, I'm just kind of rushing here. I'm going to make the slides available. If people want them, the talk is also recorded, so you can kind of take your time going through this and pause and stare at the pictures if you want. But the bottom line here is the toolbars is the original execution booting from a snapshot. Now remember, snapshot is already much faster than booting from scratch, right? And the bars on the right-hand side is the execution with our technique called record and replay. Okay, and so you can see that we're accelerating cold starts by about 3.7x by very quickly mapping the function working sets from storage, could be over the network or from local disk into main memory. Okay, we eliminate the vast majority of page faults. The entire technique is implemented in Linux using user level page faults. So it's actually existing support in Linux. All of this is open source. Actually, this idea Amazon took and integrated it into their stack. So Firecracker is Amazon micro VM, one of their sort of fairly recent sort of updates has been integrated that sort of a technology. They did their own implementation, but the idea came from us. And I think that's it. A lot of people worked on this. The lead for this entire project has been Dmitry Stugov, who graduated, got his PhD in my group. He's now at ETH. And we have a massive research community, lots of users. We would love to work with you guys. We can help you use these technologies. Please reach out, and I don't know if there's time, but happy to take any questions.
Thank you, Professor Boris, for an informative talk. We can take a few questions.
Please.
Yeah. So from your analysis of even the cache faults, fetching times, as well as the page faults, it's kind of clear that having the serverless model where you have a lot of functions and libraries which are redundant, like multiple copies of those loaded.
Yeah.
Instead of having just a like conventional model where you just have the processes, multiple processes, and the libraries are shared. So is there some analysis where to show that, okay, in these cases, it makes sense to stick with the conventional model, and only in these cases you have benefits of going to serverless, where you have multiple replicas of the same, almost a system image loaded for running the functions?
Sorry, I'm not sure if I understand the question. So you're asking about the redundancy across different like functions or VMs because the same libraries are being used, or is that what you're asking about?
Yeah, so you would, like, if you're running multiple function instances, you'd be loading the libraries multiple times, and there is inefficiency because of the instruction fetch times, as well as even if you're using snapshots, you're
right. Okay. I see what you're saying. So right. So there's been a lot of work over the years looking at deduplication, at least in the context of a particular server. So there is the duplication across virtual machines. So for example, if there are parts of the stack that are being read-only parts of the stack that are being used across VMs, they can be deduplicated. So essentially you can use kind of the same bits of memory across virtual machines. There are a lot of kind of security concerns around this stuff. So generally speaking, I think today, providers, cloud operators, they just bite the bullet and they accept the fact that a lot of memory is being wasted on duplicate libraries and duplicate kind of memory because of what you said. Everybody's using the same libraries and so forth, right? And so they favor security over everything else. But I completely agree with you. I think there are a lot of opportunities for sort of deduplication, mostly to reduce the memory footprint of this stuff. That's kind of the main reason why you would do this, is so that you need to fetch less stuff over the network and you consume less memory on a particular server.
Thank you.
Yep. Yeah, please go ahead. Just speak up because Yeah, I can't really see the question.
So two questions actually. So the first is that how do you decide that I want to use serverless architecture for certain, application and maybe not for some other, right? As a cloud provider, I mean, is there a decision made by the people who are, writing application for the cloud provider?
Yes. The developer, as a developer, you are completely in control of this decision because you're basically writing an application, right? You need to package it up. You kind of need to make it work with a particular cloud operator. So you're fully in control of this. So I can tell you my personal thoughts on this. So essentially, we have to decouple the technology from the cost, right? Financially, I think technology is great, but the financials of it, which are they have nothing to do with engineering. That's just what the cloud providers charge. The financials of it basically dictate, as I said earlier, if you're going to spend a lot of continuous time processing something, right? Like you need to analyze a huge data set and you're going to spend half an hour doing it, right? Or you have a popular website and you're continuously nonstop serving traffic, like nonstop, right? Serverless is probably not the right model for you. It's just not cost effective, right? This has nothing to do with research, engineering, whatever. This is completely cost, right? But if you occasionally need to do something, right? Like you need to occasionally, invoke some sort of a service, right? Now remember, this stuff is compatible. Like I can be running a website in a virtual machine and that's running permanently, it's like my service is always up. But occasionally I need to do some additional processing. I need to invoke something, right? Like somebody, uploads an image and you want to compress it. You can invoke that additional functionality as a serverless task. So all of this stuff is compatible. So anything that runs occasionally and not for too long is a really, really good model for serverless from a financial perspective.
So to go back,
does that help?
Yeah. So to go back to your motivating example of say, like say big billion sale of Amazon or something, right? Suddenly there's a surge in sale for like say 3 days,
Yeah.
But then it's going to be sustained traffic, right? I mean, so is there a good model for serverless or not? I'm a bit confused there.
So if you're talking about the Amazon store, given their volume, well, okay, Amazon owns their own infrastructure. So the cost, again, we have to differentiate the cost that they expose to users because Amazon AWS, Amazon Cloud wants to make money. It has nothing to do with their internal cost.
Right. Agreed. Yes.
So the Amazon store, I have no idea how they run. Maybe for them, the whole thing being serverless makes a lot of sense. But as a user, right? You really need to look at the cost. Like if you have something at massive scale, and you're constantly serving queries, the serverless model, I can actually point you to a paper that does this sort of analysis.
Sure.
Analytics, right? The paper is not from my research group. It's from another group, right? And they basically show what is the query rate, like how many queries do you need to be serving in order for serverless to be cost effective. Right?
Okay.
But again, I want to say this is not engineering. Like a lot of these financial stuff drives sort of research and engineering decisions because you kind of have to make stuff cost effective. But actually, we need to sort of decouple the serverless execution model from, hey, when is serverless actually cost effective? And these are a little bit different things.
Right, understood. And second thing was that and see these functions are also written by developer themselves, right? That's my question. I mean,
absolutely. Yeah. So as a developer, exactly. You write the user code, right? You decide as a developer how to break up your application into functions, right? So nobody tells you how to do that, right? And so you decide on the granularity. Do you want 2 fatter functions or 4 sort of slimmer functions, right? So you make that decision completely yourself.
I mean, this is also sort of important, right? Because if I have 2 like slim functions, then I probably write too much to database and then I have to read it back. And if I
exactly, you nailed it. Exactly, you nailed it. So this is becoming a research topic. This is something that my group is looking at, is essentially how do you automate or how do you help the developer with this type of a decision making? Absolutely. Yeah, right now, I don't think there are good tools to help people do that. Yeah.
Okay, thank you. That's all I got. That's all I want.
Sure.
Hi, my question is regarding the last graph. With the page prefetching, why it seems like the VM startup times have increased? That blue.
Yeah. That's a good question. So you're absolutely right. It looks like VM startup time is increasing because we're doing all of this loading up front, right? So we're going to basically load a bunch of stuff from memory, and then we're going to allow the function to run. And the reason we do that is because we only have a limited set of cores, right? We're not paying for more cores. This is essentially part of function execution, right? So if my function runs on one core, because that's what I pay for, I need to use that core to first load the VMM and the snapshot, right, using my technique. And then I'm going to start the execution.
So the saving is in not waiting till the page fault to fetch it, but we fetch it at during the startup of the VM itself, all the pages.
Exactly. So I'm going to kind of pay this cost up front, right? And so I'm going to increase the VMM load time. But then, because I did this with high concurrency, right? So I read a bunch of stuff like kind of quickly from this. So serially, in the sense that it's not one by one, but I do this like kind of exploiting contiguity, spatial locality in disk accesses, right? So I just kind of like read a bunch of stuff, I page fault it all in, and then I have much better performance during the execution.
Okay, thanks.
Yeah, good question.
I had one question, sir. Like, is serverless always associated with the functions as the execution model? Would people be interested in looking at serverless for the opportunity it provides with regard to not specifying how the deployment attributes go? What's your thought on that?
Sorry, can you clarify? What do you? Yeah, can you clarify a bit? So,
as part this lecture, you have been focusing on function as a service model. And the idea here is that the developer only writes the function, does not talk about what kind of size in terms of the CPUs or the memory that is required by the function, except for the fact that he would say whether he could make a selection of the pre-established sizes associated with a given function execution. But one of the important features that serverless also brings in is that unlike the containers or the VMs, where you need to size the VMs in accordance with the execution workload that you are going to host. So is that a feature that serverless could be exploited with a different execution model, like, for example, persistent services, which need not have the attribute of resources being specified for deployment?
So, wow, I'm still not sure if I completely understand the question. I'm sorry. So I guess you're asking about kind of upfront resource reservation, right? Me saying that I want 2 CPUs and like 128 megabytes of memory. Is that correct?
That's partly correct. So, so by serverless, I mean that I do not want to specify where and how big the machine should be on which I would like to deploy my execution. So is that a property that is worthwhile exploring? Because function as a service has a limitation in the sense that it has a short execution time.
Right.
It is event driven and so on and so forth.
Yep.
But let's say, for example, I think this is continuing on Parimal's question. How are you sure that it should be a function as an execution model? Or what happens if I would also require a longer execution times for functions? Like, say, for example, I want to host one of the network functions in using a serverless paradigm. And I may not want to actually be worried in terms of specifying what the deployment artifact should look like. Can the framework or the serverless framework take care of that
I see. I think I understand what you're saying. So again, so I think you're asking about why should the user specify the number of cores and the amount of memory, right? Why can't it sort of like, here's the code I want to run, just like run it for me. Like you figure out, what is the right CPU type. Is
Right.
that what you're saying?
That's correct. That's correct.
Okay. I understand. Yeah, that doesn't happen today. I think it's not a bad idea. And I think there's a body of research that could be used to make quote unquote recommendations as to where things should run. Again, like some of the research we're looking right now at automating, essentially kind of saying, I have this functionality, like how many different functions should I have and so forth. We're also thinking about kind of what are the cheapest instance types, for example, that you can have to do that. So right now today, the developer has to make these decisions and they'll probably go conservative.
Okay.
I think that while automating these decisions is probably possible, essentially having some sort of an analysis framework that says, yeah, the right instance type for you is that. I think that in the near future, I suspect that you will need to reserve some resources, basically explicitly tell the provider, hey, I want this concurrency, or hey, I want this much memory, because that is how they can, that's how the provider can basically figure out how much they can pack in a server, right? Because if your function potentially has, very high fluctuation in memory usage, that actually not just complicates their job, it actually becomes very sort of risky for them to pack a lot of stuff, because all of a sudden your memory usage explodes. And what do they have to do to like all of the core running things, right? They're out of memory, they have to swap them out, they have to shut down other functions. So by making you, the user, say, this is the most memory I'm going to use, that's how they get determinism that allows them to pack a lot of stuff.
Correct.
I just want to share, there is a body of work from Stanford University by Dr. Neerija, where they look at model serving, using serverless. And so they tell you what model basically the popular model and what kind of latency you are looking at. So based on that, they choose the right type of instances to deploy the model. So then it will become, serverless. You don't need to really specify the resources for your serverless function, but you define your requirement, how fast you want that piece of model to run. And accordingly, the selection is done. Yeah, so there is a body of work already been going on in the space. Yes.
Right. But I assume you would do this a priori. You're going to make this decision, right? Kind of offline, so to speak, right? And you're still going to tell, AWS or whatever, like this is what I need in terms of resources to run things as fast as I need them to run.
Yeah, so maybe that's their platform could be a middleware between user and the hyperscaler.
Yeah, I agree.
Possible.
That would be cool.
Yes. Yeah.
Thank you, sir.
Of course. Yeah, good question. Anybody else?
Yeah, so another question. Does vHive have any support for, say, placement of the functions to optimize on communication patterns, or even the, image in the cache? The node having.
So right now we're collaborating with Anna Klimovic here, and in fact, my former PhD student is now doing a postdoc with her, and so we're looking at scheduling. So how do we do, in a cluster setting, how do we place functions in a way that basically reduce call starts, maximize performance, kind of enable very high packing ratios while delivering good predictability. So we're looking at all of these things. This is actually a fairly hot research topic these days. So that's, I guess that's kind of like the best I can tell you. I mean, people are looking at it actively. It turns out to be kind of, there are some simple heuristics you can use, but it's a fairly difficult problem with a lot of money riding on it. And so cloud providers are also, I think, exploring different scheduling policies.
So is it done as part of Kubernetes scheduler, or is it outside?
Oh, of course, yeah. So Kubernetes, exactly. So Kubernetes have a policy. So for example, I'll give you an example. AWS today, when a function instance is running, right? So it's not just like a warm instance in memory. Think about the first part of the talk, right? So I have an idle instance in memory and an invocation comes in. A load balancer or Kubernetes will kind of say, okay, let's use this instance, which is idle but in memory. Once that instance starts running, so it's actually executing an invocation, AWS chooses, it's a decision that they made, they do not queue at that instance. So if an instance is busy, they will either route to another warm instance, or if all of the other warm instances are actually processing invocations, they're going to start cold boot a brand new instance. So they don't allow queuing at already running instances. Okay, this is a scheduling decision that they made. Is it optimal? Probably not. Okay, so, can you do better? Probably yes, but this is tricky, right? If the function runs for a very short amount of time, like super short amount of time, a little bit of queuing is okay. But if a function runs for a long time, queuing is a bad idea. You're actually better off starting another instance. And so Microsoft has a completely different policy, right? Completely different policy, right? They will actually queue first, and then they'll start something up if necessary.
Mm-hmm. And if you have time, had another question. So again, going back to the networking stack. So when you mentioned gRPC, again, it's at a higher level of the stack. And then I was asking about how do you emulate the network interfaces or the network links for the containers? And there was some Infocom paper in 2018 where it showed that using the standard Docker networking has big performance penalties as high as 30 to 70%. And unfortunately, AWS and Google, you don't get to know about how they are emulating the lower levels of the stack. Is there any insight or like?
So yeah, so this is not something we've touched, right? So we use off-the-shelf stuff with kind of standard networking functionality that comes as part of the micro VMs that we use, and standard Linux. So yeah, that's not something we've touched. I'm not surprised to hear that there are inefficiencies, but yeah, we haven't looked at that.
Mm-hmm. Thank you. And sorry, like another. Are there any new efforts on the data synchronization part, especially the fetching of images, storage optimizations within?
So for image storage, there has been work, again, not in my group, but people have looked at again deduplication. This came up earlier at a kind of operator, provider level, right? So just like Docker today. Right, if you think about it, Docker, when you fetch Docker images, right, it's not just like, holy smoke, here's like this entire giant container that has everything. It has layers, right? And so kind of deduplicating at the container sort of image store level, that some of this already happens. And people have also looked at deduplication, at kind of VM level as well, at the cloud storage level. Again, this is not something I do. I'm sorry, I wish I could tell you more about it, but I just don't know. But I know that this is something that providers are interested in to reduce their storage footprints.
Thank you.
Sure. Any last questions? Okay.
Thank you, Professor Boris. As discussed before, anyone else has any question? And as discussed before, we would like to remind the audience to subscribe to our Google Groups, which is the mailing list for information on future talks. You can also visit our website for more details. The links have already been pasted in the chat box. And the link to the recorded video will also be posted on the webpage. Thank you, everyone, and have a great evening.
Thank you, everybody, for having me.
Thank you,
Professor, for an interesting talk. And we'll reach out to you for the details on the platform.
Sure, of course. Yeah. Take care. Thank you.